In the previous tutorial, when we talked about sweeps 1, I was introducing sweeping for P&ID systems, piping and instrumentation diagrams for pneumatic and hydraulic systems. In this tutorial, I'm going to take sweeping to a slightly different application. I'm going to use it to sweep threads, external threads and internal threads. And the reason I'm going to go over that is because this is actually quite a common feature to model in the industry. So I'm going to model two standard threads using the standards from the Machinery's Handbook. So I'm going to look at the charts from the Machinery's Handbook, which is displayed here nicely for you. I'm going to read the numbers and I'm going to model those threads. So in this tutorial, I'm going to model a 3/4 10. So 3/4 is the OD, 10 is the TPI, the threads per inch. But for the final project, for the vise you have to design, you're going to follow this. Okay, you're going to follow this size, 1/2-13. So you're going to follow the same tutorial here today. The only difference is you're going to use this number. So to model a thread, you really need three things. Well, first of all, you need to know if it's an external and internal thread. And once you know that, you need three things. You need to know the major diameter, the minor diameter, and the pitch. You can get the pitch from the charts, but really you don't even need a chart for this. The pitch is just 1 over the TPI. So you see this 10, you just do 1 over that number and you get the pitch. So once you have these three numbers, you can model a thread. After we finish going over these steps, I want to show you three other places where sweeping is commonly used. One of them is for knurls, okay? Another one is for springs. And another one is going to be for coils. So, towards the end of the tutorial, I'm going to talk about some of the challenges and some of the benefits I had from using the sweeping tool for some of those different applications. So we're going to start with this file, which is just a start file exploded, right? It starts like this, you just explode it to open it up. We're going to start with this, and what you'll notice is there's a blank here. This is called a blank. A blank is the starting point to a product before threads are machined, and it looks like this. So we're going to start with a blank, and then we're going to machine threads on it. And it's going to look like this. Okay, that's going to be the tutorial. Couple of things I want you to notice. Did you notice this chamfer here on the ends? See this chamfer? This is really good because when you do that, you get a really clean exit on the threads. Okay, as you see here. Same with the other end. It's a very clean exit. Otherwise, you'll see it just stop arbitrarily in the middle of nowhere, and it's not going to be clean. To fix that, you can actually create another sweep, another spiral with a draft angle, and as it fades off, it gives you that same effect. That's only if you don't have a chamfer. But personally, I find it much easier to just include a chamfer to achieve that really clean exit on the thread. Another feature to notice is this undercut. An undercut is a common feature in threads so that this bolt can hit bottom on this surface. If we don't put this undercut, if we keep it the same OD as these threads, there's a risk that the threads will stop in the middle of its end because of the way it's assembled. It depends on how it's assembled, but a lot of times to avoid having that seizing to occur in the middle of the thread, an undercut is provided so that it clears off and allows the bottleneck to be the stopper on the head of the bolt. So let's go ahead and start building the threads on this. I'm going to right click and open part so I have easy access. So before I had an assembly, now I have a part. And what I'm going to do is create a sketch on the top plane. Okay, and let's take a look at what this sketch has to look like. Let's go back to step 2. Okay, it's like a triangle that points down. Very important to know where it points. This one points to the bottom, just like this. Okay, so then from here, I'm going to hit Control-8 to make my life easy. Then I'm going to add a center line that snaps to the midpoint of one end to the other. Then just to clean this up a bit, I'm going to add another center line from the midpoint of this line to that line. And I'm going to add a coincident relation to this, just because I want it to be somewhat clean. Alright, so this looks good. Looks like I can move this at an angle, so I'm just going to put a vertical relation to make this symmetrical and a horizontal one here. So this looks good. That looks good. Let's see if we can drag this. Alright, that looks pretty good. Now I just got to add some numbers to define this. So if you remember, this is the... See this? This diameter all the way through is the minor diameter. Let's take a look at the thread. Alright, this outermost diameter is the major diameter. This inner diameter is the minor diameter. Okay, so when we look at this chart, we got to first ask ourselves, alright, is this an external thread or an internal thread? This is an external thread. Bolts are external threads. So then we look at these two numbers. We look at the major and the minor, and we divide them by 2. Okay, so this number divided by 2 equals this. Okay, and then this number times 2 is this number, because that's the minor diameter. As far as this 60 degrees, that's standard. You don't really need to change that. The pitch is this value here is what you see here. It's P divided by 4. So let's take a look. P is 0.1 divided by 4. If I was doing an internal thread, it would be P divided by 8. Okay? So that's where those numbers come from. So now that we understand that, we're going to go ahead and plug them in on here. So for example, we said this was going to be 0.025. We said this was going to be 60 degrees. We said this was going to be, let's take a look, 0.3709. And we said that the inner one is going to be 0.3146. And as you can see, it's fully defined. That's what it looks like. So you see, we just needed the major and minor diameters divided by 2 to get these two numbers. So now that we have the profile, we need a path. If you remember, when you sweep, you need two things. A profile that looks like this, and a path that looks like that. In the newer versions of SolidWorks, you don't need a profile for pipes, because they realize that a lot of engineers need to sweep tubes, pipes, strings, and things like that, that they gave you an option to just click that so you don't have to draw a circle. But when you need something weird like that triangle I just drew, you gotta select the two. So we got the profile. Now let's create the path. And the path on a spiral, on a thread is a spiral, or a helix spiral. So to initiate that, you actually need a circle though. So I'm just gonna create a circle that is coradial. I'm holding shift to do the double select. That's coradial to the OD of that blank. And now when I hit helix and spiral on this, okay, I'm going to reverse direction, and this is where you enter that pitch. That's why the pitch was so important. Okay, let's see, 0.1, right? If I remember right, yeah, 0.1. Okay. Then let's see how many revolutions. So it's really until you hit the neck here. So it's 19.1, so 19.5, 0.1, and 0 degrees. So let's take a look. 19.5. See, that's what you get. And this is what I was talking about with the taper. Sometimes when you want it to kind of exit out cleanly, you create another helix with an angle like that so that it picks off. But again, I much prefer you use a chamfer to get that clean exit, that clean entry and exit. So anyways, that's all it is. 0.1, 19.5. Let's click OK and let's see what we get. Alright, now that we got the, the profile, and we have the path, okay, you can sweep. And a lot of times I don't even try to figure out which is which. I just control select both, and the software knows which one's which. It just knows it. However, to do the sweep, this is not a regular sweep. This is actually a swept cut. So I'm actually cutting the material from the geometry. All right, so that's the difference. This creates geometry, this cuts geometry. So I click OK, and there's the result. As you can see, I have very clean threads that start from the chamfer and exit out. Okay, as you see here. So this is a very standard 3/4 ton. If I go to Home Depot and buy a 3/4 ton thread, this is what you get. This is the exact size. There is a threading tool. Okay, no, it's not this. It's a relatively new tool. It's called Threads, and it actually generates what I created here. But the thing I don't like about the Threads tool is that it doesn't let you customize it. It doesn't let you really get the amount of control that I have over some of these little details. And another reason I like using this technique is because in this technique you have to really understand the numbers from the industrial textbooks, and only when you understand those numbers and those parameters can you really optimize your designs, okay? Because that's what engineering is. A lot of it is understanding how to build from the raw materials. It's not being able to click a button and have everything work in one shot. A real engineer is someone who can build the things from the raw materials, can build from scratch. That's what it is. Like, for instance, when you ask someone to build a website, you know, if someone says they use WordPress, it's a bit of a joke, because that anyone can do that, you know. Or it's like saying you're a programmer because you know how to use Excel. There's nothing to that, you know. The real engineering is behind building something from scratch, from the building blocks, from the elements, from the laws of physics. Okay, so now what I'm gonna do is include the threads on the nut, and these will be internal threads. So guess what? It's actually going to be pretty much the same thing as what I did on the external bolt. I'm going to create a sketch that's going to look like this. And as you can see, there's not a lot of information given because it expects you to kind of follow the previous steps. But again, since we're working with an internal thread now, we are just going to use these numbers. So it's the same thing. The only difference is we're going to use these numbers. Same pitch, same everything. And actually, you do want the same pitch. If you do not use the same pitch on the internal and external thread, then it's never going to fasten all the way. It will seize at like a few threads. So, and that could really damage your assembly. So always use the same thread pitch on an internal and external thread. So anyways, if we use these two numbers here on our sketch, we're gonna get this, and this is what I'm gonna do. And if you notice, the triangle is now pointing upward, and you will also notice that it's not p over 4 anymore, it's p over 8. So those are some of the other differences you gotta think about. Alright, so as you noticed on the tutorial, the triangle is pointing up, and I'm gonna draw a center line, same as what I did on the external thread. I'm just gonna set this up a bit so we can get going. So I'm going to add a center line that's midpoint to midpoint, as you see here. This looks good. Let's see. Ooh, okay. I don't know. Oh, it's because of the planes. Okay, this is seen as horizontal. It's just a little. Anyways, so this is the minor diameter, 0.3262, and this is the major diameter, which is 0.375. So again, I'm just looking at the numbers from the chart, and this is where these come from. You divide those by 2, and that's what you get. And the pitch, oops. Then we said the pitch is 0.0125 or 0.013, or the well, actually I should 0.1 divided by 8, which is 0.0123. We said every thread is going to be 60 degree, and there you have it. See how it's fully defined? See how it's all black? It means we're done. Okay, so I'm just gonna do that, and that's it. So we're gonna exit out of that. Okay, so now I need to create my my spiral. So what I'm gonna do is coradial, and I'm going to add the spiral on this sketch, and I'm just gonna go all the way through. No harm in that, but remember, gotta keep the same pitch. Alright, looking good. Okay, so remember, don't even bother what's the profile, what's the path. Just control select both and hit swept cut, and it's gonna figure out what's what, as you can see here. Okay, so we were pretty successful at this, but let me just give you a pointer. Sometimes it may not work right, and one of the reasons for that is, see the spiral? See where it starts? Right now it's starting where I drew the sketch. See, here is my profile, here's my spiral. You see how it's starting exactly where it's at? Sometimes when it's not starting there, it gives you an issue. So to troubleshoot that, you gotta play with this number. Okay, you gotta do 90, 180, 270, whatever. So just a little pointer, in case if it doesn't build. Play with that number so that it starts with where that sketch is. I'm sorry, I made a little mistake here. This was supposed to be 0.375. Okay, that's a lot better. Okay, there's the threads. So now let's go back to the assembly. Let's see what we get. Alright, this is what we get. Now let's move this a little bit. Alright, this is very important. Look at this profile. Do you see how there's a gap in the internal and external threads? Look at this gap. This is really good. You want a parallel gap like this, and it goes consistently all the way through, and this is where it starts. Okay, this is a very clean thread engagement. For the project, I even encourage you to add a little bit more of a gap, just so that it clears really well. Okay, because FDM3 printing is not very precise, so you may want to add a little bit more of a gap. But these are the nominal numbers for a 3/4 10. Okay, so that's a good thread. The numbers are right. Okay, so this is good. So now I want to move on to a slightly different application, which is a knurl. A knurl is a commonly used feature in machining to add more grip to a tool, and a lot of machinists are familiar with how to machine this. There's these roller stamps that kind of crush the profile onto the surface. But a lot of engineers are interested to know how to model these, and there's many ways you can do this. One way is to use a texture. You can just paste the texture, and it will probably be more efficient than trying to model it from scratch. Or you can do this using the sweep cut tool. So let's go back in time here, and let me show you how this is done. First, you have your cylinder. You add a chamfer. Remember, add that chamfer to clean off the edges. Then you do a swept cut. All right, just like we talked about. A swept cut. The only difference is the pitch is really high. It's so high that it's almost like a 45-degree line. What I mean by that is the spiral. You see the spiral? It's so stretched out that it looks like it's a 45 degree. So there's the spiral. There's the initiator for the spiral. And then I'm drawing a triangle. Okay, so there's a triangle. It's a very small triangle. And then I have a spiral here. Okay, so that's how you start. And then you need to pattern that. Circle pattern that all the way around. And you could even use this for like a cutting tool for modeling the flutes, the cutting flutes. Okay, but a knurl is pretty much a cutting tool like this, only you mirror the pattern on itself. You see, you mirror it on a plane within its axes, and it gives you this effect. So it's really that simple. It's just 3 steps. Swept cut like we talked about, pattern that cut, and then mirror it within a plane on its axes, and you get the knurl that you want. And you can modify this any way you want. If you add more instances on your pattern, you'll get a much more granular knurl. Or you can even change the profile of the cutting surface. So you can really customize this any way you want. Another common application in sweeping is the spring. I've had to work with hundreds of springs over the years, and I wanted to share some experience with these. First of all, I'm going to talk about how some of these are built and then how you spec these on a typical engineering project. So first of all, this is a very interesting kind of spring. It uses a composite curve. Composite curve is kind of like a 3D sketch. You can create a bunch of 2D sketches and combine them together to create a composite curve. So in a way, you can build a 3D sketch from scratch using this tool. So you have two ways of doing the same thing. Then what you have is a sweep. Okay, you're sweeping this composite curve together to get the effect that you see here. And a lot of times, some engineers like to know if you can compress or uncompress these. And you can do that. If you change the pitch, right, you can change how this looks, whether it's compressed or not compressed. And you can bind that pitch to a configuration. But let me show you how working with springs is typically done on a project, because it's really rare to design a spring from scratch. A spring is a very off-the-shelf item, and 99% of the time you don't really build your own spring. I mean, there's a custom spring maker out there. I've worked with a machine that made custom springs, but it's just not the way you do things. Usually you go to a catalog and spec a spring off the shelf. So when you want to spec a spring, you got to know which suppliers to go to. I knew hundreds of different suppliers for specialized hardware, and I knew maybe 3 or 4 for springs. And one of the reasons I really like McMaster is because you don't need to buy 100 springs for just one. Alright, if you just need 1 or 2, you don't need to buy 100 springs. You can just buy 1 or 2 and you're fine. And this is why I really like McMaster Car, because I never liked storing inventory, and it's so easy to do that as a design engineer because you just need so many different parts. So I like how you could just buy one and you can customize it any way you want. So first you gotta understand what kind of spring you want. And I used to read a lot of technical reports, and I used to be subscribed to a bunch of engineering magazines, and I always liked to see what else was out there. And sometimes when you're restricted on space, these wave discs are really nice. They work just like a spring, but they're condensed, and they save a lot of space. So this has helped me out over some projects in the past. But anyways, let's say you're trying to spec a regular spring like what you see here. Now, springs can be very picky. It can be kind of a juggling act. You'll be spending hours jumping from one spring to another because there's a lot of things you got to consider. I mean, you got to think about the compression length, the compression force, the diameter, the material. Okay, you're really restricted on so many things because when you look at your machine, you only have so much space, and there may be like some sort of electrolyte chemical that may corrode the spring, and then you got to think about the force. I mean, some of these springs can lift a car, and you don't want to buy the spring and realize you can't even move it with your hand or something like that. So that's happened to me a lot of times. I'd buy a spring and it was just too stiff, and it was a mess. So you got to really spend a lot of time. Sometimes you do have to do a little bit of math and a little bit of assessment, and you got to really review a lot of data sheets to make sure that you know what you're buying. But anyways, let's say I wanted to buy this one and I wanted to specify it onto my machine. So I'm going to go ahead and open it. One of the nice things I like about springs in SolidWorks is that they do a nice job with the way they design the model. They use a lot of equations and relations that can really help you out. Like, for example, if I change this number, okay, watch how it updates the whole assembly. So that's what I would do. In a lot of designs, I would actually bind that distance, right? I would bind this distance to my configuration, and in this way I can set it to different states. Alright, let's say I'm designing a machine and I want to show it extended, compressed, loaded, unloaded, running mode, and things like that. And you can do that with configurations with the click of a button. If you want this done dynamically, I've seen that done with restraints on an assembly. Some students, they sometimes have bound the ends of a spring to the vertices on other parts of the assembly, and then dynamically when they move it, the spring moves with it. But unfortunately, it doesn't refresh real time. You gotta hit the rebuild button anytime you change it, so it's not super convenient. But personally, I've always had a lot of successes with just using configurations here. Also, another key difference with the two springs I showed you is that this is a compression spring, meaning it constantly pushes, whereas a extension spring like this constantly pulls. Your muscles are like an extension spring, but I've rarely spec'd these on my machines. The compression spring is a lot more popular because it tends to work out much better for most applications. Finally, what I want to talk about is using sweeping on a coil. This is some kind of coil you'd see maybe on a motor or on an electromagnet, and it looks like a button just helped you generate all this in one shot. But no, all this was done by hand using techniques we already knew. So for example, if I were to go back in time, this is just a spiral. This is just a spring. You use a spiral, you set a circle, and you sweep the two pieces. Then to build the kind of the wrapping wire, you got to build a structure like this. This is just a construction sketch with an offset, all right? You just put a bunch of radial lines on two circles, and then you trim the excess, and you offset that at a certain distance. Then from there, you got to stitch, all right? You create a 3D sketch that connects, all right, that construction sketch. So you go one node, then you snap to the bottom, across, up, over, down, up, across, over. Okay, you see how you're kind of slightly indexing one square at a time? So you kind of just do that all the way around, and it gives you a 3D sketch that you can sweep with these two sketches. So just wanted to show you a different technique of building. Okay, so again, there's no magic to this. I did not use a button to generate this. It was very tedious, but I just went one node at a time and just went all the way around to build what you see here. So really just understand that mix and matching what you already know can let you really build anything that you